Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Ardi Seto Priyambodo, and I am from Universitas Negeri Yogyakarta in Indonesia. Today, I'm excited to present our paper titled Schema-Guided LLM-to-Action Framework for UR5e Pick and Place Simulation. This was a collaborative work with my college, Octav Agnidewa, Gilang Nugraha Putu Pratama, and Faris Yusuf Bakhtiar. In this presentation, we will explore a method to make language control robot much more reliable and safe. Here is the outline for my presentation. I will start with the background and motivation for this research. Then I will introduce our main contribution. Next, I will walk you through the system architecture and experimental setup. After that, I will present the key result and performance of our framework. We will then look at failure analysis and mitigation strategies we develop. I will also show our end-to-end execution result in Webbot simulator, including the video. Finally, I will conclude the presentation and discuss our plan for the future. All right, let's begin with the background and motivation for our research. On one hand, we have the promise. The combination of LLM and robotics is transforming the field. They offer key benefits like making interaction with robots more intuitive and flexible. We can plan tasks faster and collaboration becomes much more seamless. However, on the other hand, we have the challenge. We call this the reality gap. The main problem is that LMM can be unreliable and inconsistent. They can produce output that are illogical or even unsafe, and they struggle with ambiguous instructions. And that leads us to our motivation. Our goal is to bridge the gap between the generative power of LLM and the reliability required for real-world robotic application. So, to solve the reality problem, we introduce our main contribution, a schema-guided framework. So, how does it work? Think, uh, think of a schema as a very strict set of rules. These rules define all the allowed objects, action, and constraints in our robot's world. This schema then guide the LLM. It forced the LLM to break down a high-level instruction into a perfect structure format every time. This approach gives us three key benefits. First, it enhances plan validity. This means the output from the LLMs is always a valid command that the robot can actually perform. Second, it improves interpretability. Then the structure output is predictable and very easy for the system to understand. And most importantly, it is increases the reliability. This creates a robust bridge between flexible human language and the precise commands a robot needs to work safely. This is the slides show our complete system architecture. I will walk you through the journey of a single command from the user input to robot action. First, let's look at the workflow overview. Everything starts with the simple text command from the user. This command is then sent to our core processing block, which we call the LLM and validator pipeline. So what happened inside the pipeline? First, the prompt builder prepared the command for the LLM. Next, our schema-guided LLM process the prompt and generates a structured JSON output. Then this output goes through a two-step validation stage. The JSON validator checks if the structure is correct, and the feasibility check confirm that the object and destination exist in the scene. If a plan is valid, it moves to the command executor. Finally, we have the execution in simulation. The command executor takes the valid plan and call predefined function like pick object and place to create to control the robot arm in Webbot simulation. So as you can see, it is a robust pipeline that ensure only valid and feasible commands are ever sent to the robot. So let's take closer to look at the experimental testbed where our system operates. As you can see in the picture, our entire experiment runs in a Webbot's R2025 simulation, which is a high fidelity environment. In the center, we have a UR5e robotic arm. The robot task is to pick and place the object. In the environment, there are 7 different objects on the table, like a can, a mouse, and a pawn. The target are the 3 colored crates, blue, green, and red. And to make sure the robot place object in the exact same spot every time, we use a special technique. Each crate has a predefined joint space configuration, as you can see in the table 2. You can think of this as a safe position for the robot's arm, which guarantee that every placement is repeatable and reliable. Now we have seen the setup. Let's dive into the key result and performance of our system. First, a quick look at how we test it. We evaluate the system using a set of 81 natural language instruction for each model configuration. To make it challenging, this instruction cover 10 different linguistic categories as shown in the table 3. And we test everything with 3 different LLMs. Now for the result, which were excellent. Our schema-guided approach achieved over 90% exact match accuracy and importantly, 100% feasibility. This means the plan it generate were not only correct but could always be executed by the robot. Our key insight is that the schema is the main reason for this success. Forcing the LLM to follow a strict structure is what makes it so reliable. We also found that the fallback mechanism plays an important role as a safety net. It helps recover from ambiguous command, but it was not needed very often for the stronger models. Finally, our framework was clearly superior to the baseline method. The rule-based system was okay but not flexible. The embedding only approach performed very poorly, with only about 6% accuracy. This really shows how effective our structure approach is. Of course, no system perfect. So in this slide, we will look at our failure analysis and how we mitigate those failures. First, the analysis on the left, we found that the system struggles with two main types of the problem. The first is ambiguous reference. This is when the user says something like pick it up. The system doesn't have the context to know what it is. The second problem is missing color, where a user doesn't specify a destination, so our system is forced to guess. To solve this, we propose a simple but very effective mitigation strategy, an interactive clarification dialogue. Instead of guessing, the system just ask a question. For example, if the user say pick it up, the system will ask which object should I pick up. This simple interaction successfully resolved 100% of this critical failure in our test. Now, if you look at the chart, it shows the different types of errors. You can see in the baseline method like embedding only fail a lot, mostly on feasibility. But I want to highlight the key insight about our hybrid model. We found that we call scoring asymmetry. That means that even when the system first attempt to parse a comment is wrong, our fallback system can still recover a usable, feasible comment 28% of the time. This demonstrates that our system has a high practical utility and can recover from its own mistake. So after analyzing our system performance, we want to put it all together and test it from start to finish. This brings us to our end-to-end execution in Webbots. To do this, we perform a plan and execute verification. We took 5 distinct instructions, as you can see in the table 7, and run the full language to action loop. And the result we perfect. We had 100% success rate as summarized in the table 8. All 5 instructions were correctly parsed and executed flawlessly by the robot. Most importantly, every execution was complete without any collision or graph failures. Down here, figure 4 show you what 2 of these successful trials look like, following the standard approach: grab, pick, transfer, and place sequence. This leads to our overall validation. The successful test confirm our central claim that a rigid schema can really be reliable and safely map simple text commands to real robot action. The picture on the last slide give you a good idea on the process, but show you how it all works in real time. I have a short video of the system in action. In this video, you will see the full process. I will type a comment into the user interface on the left. The system will then parse this comment, generate a plan, then execute with the robot in the Webbot simulation. Uh, let's watch the video. Okay, this is the manual control, so we can move the robot uh, with the press the button like pick can, pick mouse, pick phone, or uh, every object, and we can place the object to the defined uh, box with the button also. And then I will demonstrate with the our method. I will give the instruction, pick the can, and move to the blue box. And after click generate and execute, the scheme will be generated. Then if the visibility is okay, then the action will be executed. I will try the other instruction like move the mouse to the crate, and then yeah, like in the video, it's success to move the mouse. Uh, it's success move the mouse to the red crate. So to conclude my presentation today, I'd like to summarize our key achievement. We successfully demonstrate a SIM-guided framework that significantly enhanced the reliability of LLM-driven robotic control by enforcing a rigid JSON schema. Our approach achieved over 90% exact math accuracy and 100% plan feasibility with top models. Our hybrid architecture proved to be superior to the other baseline method, and we validate its practical use through successful end-to-end execution trials in the simulator. So what's next? We are excited about the future of this work and are focusing on 3 main areas. First, sim to real transfer. The next big step is to take the system out of the simulator and deploy it on physical robot. Second, scalability. We plan to expand the framework to handle more complex multi-step tasks, not just a single pick and place action. And finally, efficiency and benchmarking. We will explore using local models to make the system faster, and we'll compare our approach against other modern methods like native function calling APIs. Before I finish, I would like to take a moment to acknowledge the support we received for this project. This work was supported by Universitas Negeri Yogyakarta through their internal funding program for research group. We are very grateful for this support. And that's bring me to the end of my presentation. Thank you all very much for your time and attention. I will now be happy to answer any question you may have.